clock latch and flip-flop circuits. Clocked SR latch. All of the SR latch circuits examined in the previous session are essentially asynchronous sequential circuits which will respond to the changes occurring in input signals at the circuit delay dependent time point during their operation. To facilitate synchronous operation, the circuit response can be controlled simply by adding a gating clock signal to the circuit so that the operating outputs will respond to the input levels only during the active period of the clock pulse. For example, reference the clock pulse will be assumed to be a periodic square waveform which is applied simultaneously to all clocked logic gates in the system. The gate level schematic of clock NOR based SR latch is shown in figure. It can be seen that if clock Sk is equal to logic 0, the input signals have no influence upon the circuit response. The outputs of the two AND gates will remain at logic 0, which forces the SR latch to hold its current state regardless of the S and R input signals. When the clock input goes to logic 1, the logic levels applied to the S and R inputs are permitted to reach the SR latch. The possibly change in its state. Note that as in the non-clocked SR latch, the input combination S equal to R equal to 1 is not allowed in the clocked SR latch. With both inputs S and R at logic 1, the occurrence of clock pulse causes both outputs to go momentarily to 0 when the clock pulse is removed, that is, when it becomes 0, the state of the latch is indeterminate. It can even eventually settle into either state depending on the slight delay differences between the output signals. To illustrate the operation of the clocked SR latch, a sample sequence of Sk, S and R waveforms, the corresponding output waveform Q are shown in figure. Note that the circuit is strictly level sensitive during active clock pulses, that is, any changes occurring in the S and R input voltages when Sk level is equal to 1 will be reflected onto the circuit outputs. Consequently, even a narrow spike or glitch occurring during an active clock phase can set or reset the latch if the output loop is shorter than the pulse width. Figure shows a CMOS implementation of the clocked NOR based SR latch circuit during two sample AOI gates. Notice that the AOI based implementation of the circuit results in a very small transistor count compared to the alternative circuit realization consisting of two NOR 2 gates. The NAND based SR latch can also be implemented with gating clock input as shown in figure. It must be noted, however, that both input signals S and R as well as clock signal Sk are active low in this case. This means that changes in the Changes in the input signal levels will be ignored when the clock is equal to logic 1 and that inputs will influence the output only when the clock is active. That is sk is equal to 0 for the circuit implementation of the clocked NAND based SR latch. We can use a simple. Here you can see the figure gate level schematic of the clocked NOR based SR latch and figure simple input and output waveforms illustrating the operation of the clocked NOR based SR latch circuit. Figure AOI based implementation of the clocked NOR based SR latch circuit. Here you can see the figure gate level schematic of the clocked NAND based SR latch circuit with active low inputs. Here you can see the figure A gate level schematic of the clocked NAND based SR latch circuit with active high inputs. B partial block diagram representation of the same circuit. OAI structure, which is essentially analogous to the AOI based realization of the clocked NOR SR latch circuit. A different implementation of the clocked NAND based SR latch is shown in figure. Here both input signals and the SK signal are active high. That is, the latch output Q will be set when SK equal to 1, S equal to 1 and R equal to 1. Similarly, the latch will be reset when SK equal to 1, S equal to 0 and R equal to 1. The latch preserves its state as long as clock signal is inactive, that is when SK equal to 0. The drawback of this implementation is that transistor count is higher than the active low version shown in figure. Thank you.